Hello everyone, we're back. My name is Nicholas Wiley. Today what we're going to be doing a von Neumann stability analysis on the partial differential equation we've been using in the past couple of videos. So the first thing I want to discuss is our partial differential equation. If you look over here, this is the equation that we found, I believe that was last episode, yes. And this was through, this was the first equation that we ended up with in the first video, and then over here we have our explicit differencing, what we ended up with by doing that. Now, in addition, something else that we have that's new to us is this right here. What this is the solution to our partial differential equation that we have over here. Now, I'm not going to go through exactly how we got here. It's very, very complicated, and there's really no need to do that. Just to save us some time, we're just going to have it here, and what we're going to have to do is we're going to have to work this along with our explicit differencing equation. We're going to find out the solution, the set of solutions to our explicit differencing equation. Specifically, what we're going to be looking for is we're going to be trying to figure out why our delta t value must be less than or equal to 0.5, our step. If you remember at the end of the last video, what we ended up with was a graph that sort of looked something like this. A bunch of different valleys and peaks, very high numbers, and we're going to try and figure out why that is. And what's going to lead us there is this understanding of this value k, if you can see that right there. Now what k does is it pretty much defines this set of solutions based off of our boundaries of our system that we have. Now this is done because we have the left side and the right side of the bar set to different temperatures. So k is going to help us finally get to that point where we can try and understand why our step needs to be less than or equal to 0.5. And I believe that's everything we needed to get out of the way. So what we're going to try and do is we're going to try and use the summation of these values right here, these e to the ikx, all those terms. We're going to use a summation of those based off of what we have over here, and we're going to finally be able to run a von Neumann stability analysis on our explicit differencing equation and our whole system as a whole. So let's hop right into it. Now, you see this equation that we had in the last episode. This is going to be very beneficial for us. Just being able to see this is going to help us get right into it. So I'll start by trying to define a term that we know, or a term that we can sort of talk about. Well, the first one that we should start with is pretty basic. We start with the tj, n. Now, what can we do with this? As we can see, we have the ikx, and then we have the negative alpha k squared t. Now, when we did this before, we had the fact that x is equal to j delta x, and t is equal to n delta t. So what we're going to be able to do is we're going to be able to substitute those things right into our equation. So let's go ahead and do that. So we can go ahead and just put this in right here. So we're going to have e to the I, k, j delta x, and then e to the negative alpha k squared n delta t. Now, the nice thing about this side of our equation is that this is going to stay the same throughout all of what we're doing. So let's just get right into it. Okay. So looking at this right here, this is pretty simple. We have our t, j, n, that term. Now, what happens when we move up in our position step by 1? Well, what we're going to end up with, I'll try and explain it as I go. It's a little bit finicky, but for our tj plus 1, n, that is going to equal, first thing we can do, ik j plus 1 delta x e to the negative alpha k squared n delta t. Now it's a little bit complicated to explain how we're actually going to split this term, so I'm just going to write it out and do my best to explain it. So what we're going to end up with is we're going to end up with e to the ik delta x multiplied by t, j, n. Now, if you look at this 1 right here, picture that we already have these 3 terms right here, and then these 3 terms right here for that plus 1, and then for the j, we're going to end up with this again. It's a little bit weird to explain, but this plus 1, it's the same. It's so hard to explain. It's man. Rule of exponents. When we have this plus 1 right here, we're going to be multiplying by this. So up here we have this j, this is the term that we have, ikj delta x. Then this plus 1 is going to remove the j, so we're left with ik delta x. Hopefully that makes sense. If not, maybe just try and understand, look at it. I think it is pretty self-explanatory, but you never know. So that's going to be our term for this right here. And then in addition, we also have this over here. This term is a part of tj comma n. And then for tj minus 1, I'm not even going to try to explain. I'm just going to use the same rule. So what we're going to have is we're going to have tj minus 1 comma n is going to be equal to e to the negative ik delta x tj comma n. Okay, and now I'm going to go ahead. I'll just do this live. What we're going to go ahead and do is we're going to go ahead and switch this equation up here. Make sure we don't forget about our r's. So we're going to start with, oh darn, I guess I shouldn't have really erased that. We have our r value, and then we're also going to, what I've gone ahead and done is I've quickly factored out the tj comma n term that we had before, as that was a part of every single term that we had. I've also included the r's that we have right here, in our 1 minus 2r term, which is a part of our tj comma n. Basically, all I've done is factored out a tj comma n and clean things up a little bit. Now, we have a couple terms that we can get rid of through an understanding of Euler's law. So we have this term, e to the ik delta x and e to the negative ik delta x. Now, one cool thing we have is that e to the ix is going to be equal to cosine x plus sine, plus I sine x. And then e to the negative ix is going to be equal to cosine x. Now, why is it just cosine x if we're doing a negative? Well, cosine x is an even function, so it's not going to be impacted by this negative that we have. Now, what we can do over here, since sine is an odd function, my marker's dying, let me switch real quick, minus I sine x. So what's going to happen is these are going to cancel. We're going to be left with 2 cosine. Now what's this x term? X is all that we have, or I multiplied by. So it's going to be k delta x. Get this out of the way. Clean her up a little bit more. tj n plus 1 is going to be equal to tj comma n. And parentheses, what are we going to be left with? Well, we're going to be left with 2 times r. 2r cosine k delta x. Let me erase this now. And then what we're going to have is plus 1 minus 2r. Okay, now we're looking pretty good with this. Now, one thing that we do need to realize when looking at this is a very important thing. Oh, actually, I guess I could factor out this 2r. Let's do that real quick. Let me make sure I do this right. Multiplied 2r cosine k delta x 2r, oh yes, minus 1 plus 1. I believe that's correct. That does look correct. Yes, Nick. Good job. So this is going to be a pretty good spot for us, because now we have the ability to actually go forward with our von Neumann stability analysis. So with this now, what can we do? When looking at this, the only thing that's going to matter for us for our von Neumann stability analysis is this piece right here. Now, you may be saying, Nick, why is it the only part that's important? Well, what this says is that this value right here has to be, less than or equal to negative 1. Nope. Greater than or equal to negative 1, or less than or equal to 1. So we can go ahead and make this a simple inequality for us. Sorry, I'm trying to go a little bit more live. I know it's been a little bit slow with video, but just making sure I'm recording. Yes. So what we can do with this is that this is going to be greater than or equal to negative 1 and less than or equal to 1. Let me just erase this. Less than or equal to 1. Man, all my markers are dying. Let's try a different color. Let's go blue. So what's one thing that we can do right away off the get-go? Well, we can subtract 1. That's pretty easy. Okay. So what we'll have is negative 2 is less than or equal to 2r. Hopefully you can see the blue. Might be a little bit lighter, but it should work. Cosine k delta x minus 1 is less than or equal to 0, actually. 0. Okay, so in looking at this, an important thing that we need to realize is that cosine right here fluctuates between negative 1 to 1. So what the highest value that it can have is 0 already, if that makes sense. So say that this was 1, 1 minus 1 is going to be 0, so what we can effectively do is remove this right boundary. Okay, now we're looking pretty good. So I believe what we can do, what we're going to do, is we'll divide this side by 2. So we're at minus 1. And then as I've said, this can only be a negative number that we have right here. This cosine, what's in here. So what do we want to do? What we're going to want to do, since this side is negative and this side is negative, we're going to want to flip our sign, and then we're also going to divide by this. So what we're going to end up with is 1 minus cosine k delta x. On this side, we're going to flip our sign. I'm going back to black. Sorry, this is a little bit finicky with the colors. I'm gonna have to get new markers for the next set of videos that I do. So this is what we're gonna end up with. Hopefully that made sense. So what we did was we divided by this. We flipped the signs, and we also had to flip our inequality as well. When you flip your signs, you flip your inequality. So this is what we're left with. Now looking at this, we actually have something very interesting. As I've spoken of earlier, we have bounds for our cosine. So let's think about this. If we had cosine of our x was equal to 1, or just cosine was equal to 1, what would we have? We would have 1 over 1 minus 1, 1 over 0, meaning that this would go to infinity, and we don't want that. We already saw that whole mess that we had before with all of this. So we want to limit that. That's the whole point of this von Neumann stability analysis, is we want to try and figure out what this value is, so that we can have a smooth time doing our Python coding next time. So rather than having that be at its maximum value, what if we put that at its minimum value? Negative 1. So if we have that put at negative 1, what this is going to become is 1 minus negative 1. So what we're going to be left with, funnily enough, is r is less than or equal to 1/2. Now why does that make sense? This is what we've been going for the whole time. How did we get that to be so clean? And what does that have to do with our time step? Well, if you remember, r is equal to alpha delta t over delta x squared. Now, something that we did, parentheses for clarification, something that we put into our Python coding was the fact that alpha was equal to 1 and delta x was equal to 1. So our r was effectively equal to delta t. So looking at this, what this is saying is 1/2, or rather, r or delta t, our time step if you'd rather, has to be less than or equal to 1/2. So we've effectively found our boundary that we have to make sure that we have a stable Python code and just a stable explicit differencing equation that we found. We found the limits of our explicit differencing that we've done. So I thank you for watching, and hopefully this all made sense. Stuttered a little bit, but we got through it, and I hope to see you in the next video. Thank you.